Fundamentals of statistics. As a society, we have fallen in love with statistics. I challenge you to watch the news or read the paper without seeing some sort of statistics to validate a claim. Sports statistics are part of daily conversation for millions of people. You'd be hard-pressed to find a topic that is not linked in some way to statistics. The main goal of statistics is to infer or conclude something based on facts about the population. Often it is impossible or infeasible to collect information on the entire population, so we select a representative sample and collect data on them to be able to draw a conclusion about the general population. Let's review briefly the concept of populations and population parameters to that of samples and sample statistics. In the following example, let's identify the population, population parameter, sample, and sample statistics if they exist. An AP-CBS telephone poll of 998 randomly selected Americans revealed that 6 in 10 people believe there has been progress in finding a cure for cancer in the last 30 years. All Americans would be the population of interest. The 998 Americans actually spoken to would consist of the sample. The population parameter would be the percentage of Americans who believe there has been progress in finding a cure for cancer in the past 30 years. The sample statistic would be the percentage of Americans sampled that believe there has been progress made in the cure for cancer, meaning the 6 out of 10 or 60% of the sample. Notice the population parameter is not stated. Typically, we cannot pinpoint exactly what the population parameter will be, but rather we give a range or confidence interval for which that population parameter will exist. By collecting sample data, we can infer something about the larger population in question. We will discuss confidence intervals and the margin of error later in this chapter. There are two types of statistical studies. In an observational study, researchers observe or measure characteristics of the sample members, but do not attempt to influence or modify these members. In an experiment, researchers apply a treatment to some or all of the sample members and then look to see whether the treatment has any effects. The treatment group in an experiment is the group of sample members who receive the treatment being tested. The control group in an experiment is the group of sample members who do not receive the treatment being tested. It is important for the treatment and control groups to be selected randomly and to be alike in all respects except for the treatment. For each of the following questions, what type of statistical study should be used? What is the average income of stockbrokers? An observational study can tell us the average income of stockbrokers. We need only to survey or observe the brokers. Do seatbelts save lives? It would be unethical to do an experiment in which some people were told to wear seatbelts and others were told not to wear them. Instead, we can conduct an observational study. Some people choose to wear seatbelts and others choose not to wear them. By comparing the death rates and accidents between the two cases, we can learn whether seatbelts save lives. Can lifting weights improve runners' times in the 10-kilometer race? We need an experiment in this case. One group of runners would be put on a weightlifting program, and a control group would be asked to stay away from weights. We must try to ensure that all other aspects of their training is similar. We can then see whether the runners in the lifting group improve their times more than those in the control group. Most statistical research is carried out with integrity and care. Nevertheless, statistical research is sufficiently complex that bias can arise in many different ways, making it important to examine reports of statistical research carefully. Step 1. State the goal of your study. That is, determine the population you want to study and explain what you'd like to learn about it. Step 2. Choose a representative sample from the population. This may be the most important step in any statistical study. If the sample fairly represents the larger population, then the inference or conclusion will be reasonable. But if the sample is not representative, then there is little hope of drawing accurate conclusions about the population, regardless of how careful or accurate the rest of the statistical study is carried out. Step 3. Collect raw data from the sample and summarize these data by finding sample statistics of interest. Use these sample statistics to infer or draw conclusions about the larger population. For example, if 60% of the sample believes there has been progress in the cure for cancer in the last 30 years, and this sample is representative of the population, we can then infer with reasonable certainty that around 60% meaning it could be as low as 58, it could be as high as 62% of the population will feel this way as well. Please note that we cannot directly infer that exactly 60% of the population will feel this way. We can, however, come up with a reasonable interval or range of values about this percentage of the population. The margin of error and the confidence interval will help us understand how well the sample statistic is likely to predict the true population parameter. We will look deeper into calculating the margin of error and confidence intervals later in this chapter. The last step, state your conclusions. Determine what you have learned and whether you achieved your goal. A representative sample is a sample in which the relevant characteristics of the sample matches those of the population. A statistical study suffers from bias if its design or conduct tends to favor certain results. Bias can creep into a statistical study in many ways. A poorly chosen sample, i.e., a sample that is not representative of the population, is one example. A researcher themselves can be biased if he or she has a personal stake in the outcome of the study. In this case, the researcher might distort, intentionally or unintentionally, the true meaning of the data. Let's quickly review the sampling methods. Simple random sampling is when we choose a sample of items in such a way that every sample of the same size has an equal chance of being selected. Systematic sampling is when we use a simple system to choose the sample, such as selecting every 10th or every 50th member of the population. Stratified sampling is when we first identify the subgroups and then draw a simple random sample within each group. And convenient sampling is when we choose a sample that is convenient to select. No matter how a sample is chosen, it is only useful if we have a representative sample of the larger population. Even if the sample is chosen in the best possible way, we can never be 100% sure it is representative of the population, so we may only conclude that the sample has a strong likelihood of being representative. Take a look at the following examples and let's review the different type of sampling methods that we used. You are conducting a survey of students in a dormitory. You choose your sample by knocking on the door of every 5th room. Choosing every 5th room makes this a systematic sample. The sample may be representative as long as the students were randomly assigned to rooms. If they are not, then bias could creep in. For example, if the dormitory is only of all freshmen, then we don't have a representative sample of the entire population of students. To survey opinions on a proposed new water line, a research firm randomly draws the addresses of 200 homeowners from a public list of all homeowners. The records presumably list all homeowners, so drawing randomly from this list produces a simple random sample. Recall, the term bias refers to any problem in the design or conduct of a statistical study that tends to favor certain results. Bias can occur if the sample is poorly chosen, or if the researcher can be biased if he or she has a personal stake in the outcome of the study. For experiments involving people, using a treatment group and a control group might not be enough to get reliable results. The problem is that people can be affected by their beliefs as well as by treatments. A placebo lacks the active ingredient of the treatment being tested. The placebo effect refers to the situation in which patients improve simply because they believe they are receiving a useful treatment. The placebo effect can be surprisingly powerful. In some studies, up to 75% of participants receiving a placebo have actually improved. This can be referred to as the power of positive thinking. As long as the participants don't know whether they are in the treatment group or control group, i.e. getting the real pills or the placebo, any effect arising from psychological factors, i.e. the placebo effect, should affect both groups equally. In statistical terminology, the practice of keeping people in the dark about who is in the treatment group and who is in the control group is called blinding. An experiment is single blind if the participants do not know whether they are members of the treatment group or members of the control group, but the experimenters do know. An experiment is double blind if neither the participants nor the experimenters know who belongs to the treatment group and who belongs to the control group.